It's time to continue our discussion of how to draw a graph by using information that we've learned from calculus and as well as algebra. In this particular section, we're going to be looking more closely at what it means for a function to be increasing and decreasing, and where the function is concave up and concave down. That means where the curvature has changed. Remember that concave down is down like a frown, and concave up is, well, up like a cup. We're going to take a look again at trying to find a location of the extrema values. Now, we learned earlier in this chapter that if a function has an extremum value, it must occur at a critical point. The critical points are where either the first derivative is equal to 0, or the first derivative does not exist, but the function does exist. Now, when we think about these, remember that not all critical values become extrema values. Let's take a look at a couple of types that do not result in an extremum. One of the first types would be like x cubed, that comes up, flattens, and then goes up. This point right here is a place where the tangent line is horizontal. It is a critical value where the first derivative is 0, but it's not an extremum. We call it a saddle point. There's another situation that we can have where the first derivative does not exist, but the function does. It does not correspond to an extremum value. This would be, for example, a point of vertical tangency. At one instant right here, the tangent line goes vertical. That means it has undefined slope, which means the first derivative is not defined, but clearly the function does exist there. It's not an extremum value, however. It is possible to have a place where the first derivative does not exist that is an extremum value. We've seen a couple situations like that with corners and cusps. Let's now turn our attention to the learning objectives for this section. We have quite a few learning objectives because there's quite a bit to cover in this particular section. We're going to look at how the sign of the first derivative affects the shape of the function's graph. In the last section on the mean value theorem, we found that if the first derivative is positive over an interval, the function is increasing. If the first derivative is negative over an interval, the function is decreasing. We're then going to use this idea in what's called the first derivative test for critical points. By knowing the increasing, decreasing behavior of the function and the location of the critical points, we'll be able to determine where we have relative extrema. The next thing we're going to do is use concavity, the curvature of the graph, and inflection points, where the curvature changes from concave down to concave up, or vice versa, to explain how the sign of the second derivative affects the shape of the graph. We've done this before when we studied position, velocity, acceleration graphs. When we were looking at it, we noticed that when it was concave up, the acceleration was positive. Acceleration is the second derivative. That's right. Sign of the second derivative will tell you whether the function is concave down or concave up. We're going to use the concavity test for a function over an open interval to help us draw the function more accurately. And then we're going to explain the relationship between the function and its derivatives, and use the second derivative to predict, in some cases, where the location of the relative extrema are. Let me share my screen and we'll get started. We're going to start with the first derivative test. Remember that the third corollary of the mean value theorem showed that if the derivative was positive over an interval, then the function was increasing. These two graphs that you see here, the function is increasing in both because the sign of the first derivative is positive over the entire interval. If you put your pen on the graph and trace it as the tangent line is always sloped up. However, notice that these graphs are fundamentally different. Their curvature is different. This one is shaped up like a cup. This one is shaped down like a frown. This is concave up, and this one is concave down. We need the second derivative to predict the changes in concavity, because as you can see, it makes a big change in the graph of the function. Also, based on that third corollary, we know that if the sign of the first derivative is negative over an interval, then the function is decreasing. In both intervals, the function is decreasing. Remember, you read the graph from the left side to the right side. The graph is coming down in both cases. They're still fundamentally different because their curvature is not the same. The one on the left is concave down, meaning, well, you'll learn, and the one on the right is concave up. Now, if the function is continuous, we'll have a local maximum at a point C if and only if the function goes from increasing to decreasing at point C. In other words, the only way to get a relative max or an absolute max is to be going up and then to come down. This will give us a relative maximum. That means that on the left side, the first derivative is positive, and on the right side, the first derivative is negative. Provided that it's continuous and differentiable, we know that we'll have a local max right there at point C. First derivative test also tells us that we'll have a local minimum if it switches from decreasing to increasing. If the first derivative is negative on the left and positive on the right, well, then we must have a relative minimum where the tangent line goes horizontal. This can occur only if the first derivative is changing sign as we proceed from left to right. Keep in mind that the extrema must occur at a critical point. Either the first derivative is 0 or the first derivative is not defined, but the function is defined. It's very important that you always start with the domain of the function. When we're looking at this picture right here, notice that on the left side of this orange vertical line at A, the first derivative, the slope of the tangent line, is positive. It reaches a cusp at point A. On the right side of A, notice that the slope of the tangent line is negative. This is a critical point at A, and we do have a relative maximum there. Notice between A and B that the slope of the tangent line is negative, f prime less than 0. And on the right side of B, the first derivative is positive. When it goes from decreasing to increasing, we must have a relative minimum, and we do at point B. Looking at the next change, we see that we have another critical point at C. In this case, however, on the left side, the first derivative was positive, and on the right side, it's still positive. It did not change sign, so we do not have an extremum at C. Instead, we have a saddle point. Then the function, as it approaches D, on the left side has positive slope, so the first derivative is positive. And on the left, the first derivative is negative. When you go from increasing to decreasing, you must have a relative maximum at the critical value between. Here's the formal statement of the first derivative test. Supposing that f is a continuous function over the interval I, and it contains critical point C. If it's differentiable over I, except maybe not at C. Remember, when the first derivative does not exist, but the function does, that's still a critical point. It can correspond to a cusp or a corner, or it could be a saddle. Well, no, it could also be a point of vertical tangency. Those three options: corner, cusp, vertical tangent line. Then the function has to satisfy one of these different cases. The first derivative goes from positive to negative, which indicates a local maximum, where the first derivative goes from negative down to positive, which means we have a local minimum, or it has the same sign on both sides. Then it's neither a local maximum nor a local minimum. Most likely going to be a saddle point or a point of vertical tangency. When we want to use the first derivative test, what we're going to do is we're going to find all the critical points first. Start with the domain and find the first derivative, set the first derivative equal to 0 to find those critical points, and then find any values where the first derivative does not exist, but the point is in the domain. Those become our set of critical points. We're going to use those critical points to divide the interval on a number line into smaller intervals. So the critical points will be marked on this number line. We're going to pick a test point on either side of every critical point, and we're going to compute the sign of the first derivative, not the function. The first derivative will tell us whether it's increasing or decreasing. Can't change unless it goes through a critical point. On this third step, we'll use the information from the first derivative test. If it's increasing, then decreasing, we have a relative max. If it's decreasing, then increasing, we have a relative minimum. And if it maintains the sign, we could have a saddle point or a point of vertical tangency. And then it is neither a maximum nor a minimum. Again, when we're looking at a graph, we have different possibilities. It goes from positive to negative, increasing to decreasing, it's a relative max. It goes from negative to positive, decreasing to increasing, it's a relative minimum. But keep in mind, we could have a saddle point where it's increasing, 0, and then increasing again. We can also have a point of vertical tangency, which I'll draw here. And at this point right there, it goes vertical. It's increasing, not defined, and increasing again. It does not change sign there, so the first derivative test tells us we do not have an extremum there. Let's take a look now at example 1. In example 1, we want to use this first derivative test to locate all of the local extrema for this function. It's a cubic, which means it's a polynomial, so it's definitely continuous. The requirement to use the first derivative test is that it's continuous over the domain that we're looking at, and that it's differentiable everywhere except possibly at critical points. Those critical points have to be in the domain of the function. Remember, at the end, we will substitute the x values of the critical points into the function to get the y value of the extremum. Go ahead and pause the video to find the first derivative and the critical points, then turn the video back on and we'll finish the problem together. The domain for a polynomial is all real values. When I was looking at the first derivative, I got negative 3x squared plus 64 plus 18, which does not factor. I used the quadratic formula to come up with the simplified answer of 32 divided by 3 plus or minus 7 square roots of 22 divided by 3. It will help to have an approximation for these values since we have to use them on a number line and find test points. They're approximately negative 0.278, 21.611. Probably one decimal place is accurate enough. The next thing we want to do is find out whether or not we have increasing or decreasing behavior on the interval between these critical values. We're going to draw a number line to represent the domain of the function, which is all reals. We're going to place the two critical values onto the number line as the only tick marks that we have. It does not need to be to scale. Make sure that you have some space to the left of the leftmost, space between, space to the right of the rightmost. If you have more critical points, just make sure you've got space between. Now we're going to take test points, points between the critical points, but in the domain, and we're going to find the sign of the first derivative at those points. I like to write them down and circle them so I know which ones I've used. To the left of negative 0.278 would be, well, I could use negative 0.3, but negative 1 would be far simpler. When I look for a value between these, because one is negative and one is positive, the easiest value to use is probably 0. When I'm looking at these up here, I'll probably use the test point 22. We want to know about the sign of the first derivative. The first derivative was negative 3x squared plus, lost my x, negative plus 64x plus 18. Go ahead and substitute those values into this particular derivative and see whether you get a positive or a negative number. We're not so interested in the actual value. We want the sign of the derivative. When I substitute in negative 1, it squares to become positive. So I get negative 3 minus 64 plus 18. It's very definitely negative in this region. Again, I don't really need to know what the actual value is. I just need the sign. This means that it's decreasing over the interval from negative infinity up to the first critical point. What about in between these two critical points? Substitute 0 into the first derivative. I get 18, which is clearly positive. In this region, I must have an increasing function. Now let's evaluate at 22. When you evaluate it at 22, you'll find if you substitute them in that 22 squared multiplied by a negative becomes much, much larger than the remaining terms, and it pulls it to the negative side. It is clearly decreasing up here as well. What does this mean? Well, let's draw some arrows to help us decide where the relative extrema are. The graph was decreasing, meaning coming down, and then it went to increasing at the first critical point. That first critical point must be a relative minimum. I know the x-coordinate, which was 32/3 minus 7 square roots of 22 divided by 3, but I don't yet know the y-coordinate. Let's now continue our discussion. It stays increasing here, and then when it gets to the second critical point, it changes to decreasing. I must have a relative maximum at the second critical point. I know where it occurs, 32/3 plus 7 square roots of 22 divided by 3, but I don't yet know what the value is. To find the y value at the extremum, you're going to have to substitute these nasty values back into the function itself. Let's write down what the actual function is. The function was negative x cubed plus 32x squared plus 18x. I've lost my problem. Where'd it go? Plus 32x squared plus 18x. To find the location of the relative maximum and the relative minimum, I need to find f of 32/3 minus 7 square root of 22 divided by 3. It's not going to be a pleasant problem, but it is something that, given enough time, you could work out. This is a good use for a graphing calculator, or what I like to use, which is Desmos. Let's take a look at this graph on Desmos, and I'll show you some tricks on how you can get it in there. This is a cubic function. It doesn't exactly look like a cubic function yet because I have to play with the range of it. Now, it should be cubic and it should be coming downhill, which means it can't look like a parabola. There's got to be another arm. And you can see that the arm is way over here. We have two critical values, one near the origin and one near 21.6. When we look at this particular graph, I want to know what the value is at the two critical points. I can enter those into a table, and that will get me an approximation. It won't get me the exact value, but it will get me an approximation. What you do in order to produce the table is you use function notation to name the function. Make sure that you have the of x part in parentheses. Then you click inside the box of the definition of the function and click on the gear symbol. Because it's using function notation, it will give you the option of creating a table. If you click on it, the table will be created automatically down below. It will give test points, usually between -2 and 2. In my case, I'm not interested in those points. I want to know what it is at the critical points. I entered an approximation for them, but you can enter the exact values using the normal notation for Desmos, your x coordinates. This gives us an approximation of the values of y at the critical points. That means I have a relative minimum of -2.5 at the first critical point and a relative maximum of 5,241 at the second critical point. Now, in order to see them both at the same time, you're going to have to play around a lot with the x and y range of the graph. We could set the x range to go from, say, -4 to, well, I've got to get past 21, so let's just say 24. For the y-axis, it's okay to go below, but I need to go up above, well, 5,241, so let's just go up to 6,000. Now, when I click on the graph, if I scroll in, I can see more of the detail of the graph. The problem is this relative minimum is so slight that I can't really tell exactly where it is. If you don't want these points to show up on the graph, then simply click on the solid dot with the holes in it. Then it will take them off. Desmos already wants to give you the value at the minimum, which is right there. It will also give you, of course, the intercepts. And this will enable us to find the values that we're looking for. Let's go ahead now and find the other values. Let's go ahead and write in our approximations. Negative 2.509 and 5,241.03. On an exam, I will give you one where the values are nicer and it's not so complicated to find. Let's move on to example 2. In example 2, we want to use the first derivative test to locate all the local extrema for the function, the cube root of x minus 1. Remember the 1/3 power, rational power, the denominator represents the radical index, in this case, cube root. After we're done, we'll substitute the location of the critical values back into the original function in order to find the y value at the extrema. Go ahead and pause the video, find the critical points, determine increasing, decreasing behavior, and then find the ordered pairs of the extrema if there are any. Let's look at example 2. This is the cube root of x minus 1, which has a domain of all reals because cube roots apply just as well to negatives as to positives. The derivative can be found by using the power rule and the chain rule. 1/3 comes to the front. I reduce the power by 1 to get negative 2/3 and multiply by the derivative of the inside, which is 1. This gives me 1 divided by the quantity 3 times the cube root of x minus 1 being squared. Remember that the numerator of the rational exponent represents a power like normal, and denominator represents the index of the radical. Now I need to find the critical points. There are 2 types. First derivative is 0, or first derivative does not exist, but the function does. It is in the domain. The first derivative will never be 0 because the numerator is 1, which is not 0. There is a place where the first derivative does not exist, but the function does. If I let x be 1, I get 0 in the denominator, which is not allowed. But 1 is in the domain of the function. That makes 1 my only critical value. A good test point on the left is 0. And a good test point on the right is 2. Remember that when you substitute those test points, you're substituting into the equation for the first derivative. You want to know if it's increasing or decreasing. When we substitute it on the left side, we get, I don't know how I got a negative 2 under there. This should be negative 1. The cube root of negative 1 is negative 1, but it's squared, which gives me a positive 1/3, meaning it's increasing. On the opposite side, I have 2. And when I substitute that into the function, looks like I wrote them opposite. I get 2 minus 1, which is 1. Not sure what happened to the signs there. And I end up with, again, 1/3. In other words, it is increasing on both sides of the critical point. It could be a saddle point or a point of vertical tangency. Let's take a look at the graph to see. You can see in the shape of the graph that right there at 1, there is a point of vertical tangency. The derivative does not exist because the slope of a vertical line is undefined, but the function does exist. Because there was no change in sign, there are no relative extrema. Let's now look at example 3. This is the function x squared divided by x squared minus 1. When we look at this function, we want to start with the domain. You know x squared minus 1 factors as x plus 1 and x minus 1. That tells me that the domain excludes the values 1 and -1. So my domain is all reals except those two numbers. Now what I want to do is I want to take the derivative and find the critical points so that I can find the extrema by using the first derivative test. Go ahead and pause the video, work it out, turn the video back on to check your answer. So let's compare our work. Remember that we're starting with a domain of all reals except 1 and -1. I chose to rewrite the function by moving the denominator to the numerator with a -1 exponent. In the next step, I applied the product rule and the chain rule. When I completed this, I had the difference of two terms, but I wanted one term in order to find where the derivative was equal to 0. So I got a common denominator by multiplying by x² - 1 over itself, which is equal to 1. This gave me some cancellation in the numerator, and I ended up with -2x over the denominator squared. You would have gotten the same result from the quotient rule. The next thing I want to do is locate the critical points. The first derivative equals 0 when the numerator equals 0, which is at x equals 0. The denominator will cause the first derivative not to exist, but it only does that at the values of 1 and -1, which are not in my domain. So they are not critical points. Then I write a number line with the only critical point I got as the only tick mark on the number line. I take a test point to the left of -1 and a test point to the right of +1. I substitute these values into the first derivative. Notice that the denominator is squared, so it's positive no matter what. That means the sign of the first derivative depends only on the numerator. -2 times -1 is +2, so I know it's increasing on the left. When I substitute 1, I get -2, so I know it's decreasing on the right. It went from increasing to decreasing, so I must have a relative maximum at x equals 0. To get the y value, I substitute it into the function, not the derivative. And this gave me the ordered pair 0, 0, where I have a relative maximum. Let's go ahead and take a look at that graph now. You can tell that there is a relative maximum right here at the origin, 0, 0. There is no other relative extrema in the entire graph. Notice that we have vertical asymptotes at -1 and 1, which we expected since it was a rational function. Now that we've discussed increasing, decreasing, and how we can use them with the first derivative test to locate where we have relative extrema, let's talk about the curvature of the graph. When we talk about the curvature of the graph, we're talking about the rate of change of the first derivative. The first derivative can be positive, but it can have a negative rate of change, meaning while it is still going up, it's going up at a smaller and smaller amount. This would correspond to a concave down graph. Or we can have it increasing, and as it moves across, the line gets steeper and steeper. It would be a positive rate of change of the first derivative, which would correspond to a concave up graph. When we look at these right here, it depends on whether the slope of the tangent line is getting bigger or smaller. Notice that the one on the left is concave up. The slope of the tangent line is increasing. This means the rate of change of the first derivative is positive, which means the second derivative is positive, so it's concave up. In the second graph, it's concave down. While it's true that the tangent line is always positively sloped, slope is decreasing in value, which means the rate of change of the first derivative, always positive, is decreasing, which means the second derivative is negative. It's concave down. We say that a function that's differentiable over an interval is concave up if the first derivative is increasing, meaning that the slope of the tangent line is getting higher and higher. If the slope of the tangent line is getting lower and lower, then we say that it is concave down. Let's take a look at these next two graphs, which are also situations where we have concave up and concave down, but in both of these cases, the function is decreasing. It is true that it is decreasing, and the line goes from steeper to flatter. But remember that because they're all negative, the higher negative values are actually smaller. -4 is to the left of -1/2. So the values are actually increasing, which means the rate of change of the first derivative is positive. So it is concave up. On the picture on the right, notice that while all the tangent lines are sloped negatively, it becomes more steep. But that means the slope of the tangent line is becoming smaller, since -4 is smaller than -1/2. That tells you then that the rate of change is decreasing, which means it must be concave down. Remember to use up like a cup and down like a frown in order to help you figure out which one is which. Basically, if the first derivative is differentiable, meaning the second derivative exists, then it will be concave up when the second derivative is positive and concave down when the second derivative is negative. Let's take a look at the theorem for concavity. Let f be a function that is twice differentiable, meaning we can take the first derivative and the second derivative over an interval I. If the second derivative is positive for all the x on the interval, it's concave up over that interval. If the second derivative is negative for all values over the interval, it's concave down over the interval. Now, a function can switch concavity, but as you might imagine, where it switches concavity must be a point where the second derivative is 0, or possibly where the second derivative is not defined. So we have two possibilities to look for in the change in concavity. One, the second derivative does not exist, but the first derivative does, and the second derivative is 0. Sounds like a critical point. It is a critical point, but for the first derivative. The points where it changes concavity are called inflection points. This is where it goes from concave up to concave down, or concave down to concave up. This is where the graph changes its curvature. When we were studying the position graph and talking about velocity and acceleration, these inflection points corresponded to places where the acceleration was 0. Again, we have this as an inflection point. In the picture here, you can see that there is an inflection point at A. Notice that at the far left, the graph is decreasing and the slopes are all negative, but they're becoming closer to 0. Negative numbers, the steeper it is, the smaller it is. So the rate of change is actually increasing, which means the second derivative is positive. On the right, notice that the function is increasing now, and the tangent line's getting steeper in the positive direction, which means the rate of change of the first derivative is positive, so the second derivative is still positive. At A, we have a change. At A, must have the second derivative equal to 0. On the other side of that point, the slope of the tangent line stops getting steeper and starts getting flatter again. It is true that the function is still increasing, meaning the first derivative is positive, but the rate of change of the first derivative is decreasing. So the second derivative is negative. Finally, on the far right, we have that it becomes a little negative, then more negative, more negative, more negative. That means the rate of change is negative, the function is decreasing, and it must be concave down. Let's now look at example 4. Go ahead and pause the video and find all the intervals where the function is concave up and concave down. Remember, when you're looking for inflection points, you're looking for places where the second derivative is 0 or the second derivative does not exist, but the first derivative does. Still must be in the domain of the function. Let's now look at the work for example 4 together. This is the same example that I used in example 1, so I've gone ahead and put up the information we found about increasing and decreasing here so that you can refer to it. Remember that we found that the critical points were at 32/3 plus or minus 7 square roots of 22 divided by 3, or about negative 2.7 or 0.278 and 21.611. When we did that, we also located the relative maximum and the relative minimum at the values you see here. The relative minimum was about negative 2.509, and the relative maximum was 5,241.03-ish. Now let's take a look at the second derivative. The second derivative is actually, when we apply this test, the second derivative, it becomes the critical points of the first derivative. We're taking the derivative of the derivative, which gives us negative 6x plus 64. We're looking for those critical points of f prime. The second derivative equals 0 when x is 32/3. The second derivative is also a polynomial, so it is defined everywhere. So there are no places where the second derivative does not exist, but the first derivative does. That gives us only one possible inflection point at 32/3. Remember that when you use the test point, you're now substituting into the second derivative to determine concavity. Second derivative determines concavity, first derivative determines increasing and decreasing. When we look at this, I use 10 and 11 on either side of 32/3 as my test points. On the left, substituting into negative 6x plus 64, I got 4, which means it's concave up to the left of the inflection point. On the right side of the inflection point, I got negative 2, so it is concave down. To find the location of the actual inflection point where this concavity goes from up to down, I have to substitute the x-coordinate of the inflection point into the original function, not either of the derivatives. And this gives me about 2,619.25. Let's now look at the graph and see what it looks like. This is the same graph that we graphed in example 1, but I've added the inflection point to the table. I added the exact value of 32/3, and you can see that I did get 2,619 and about a quarter, actually 0.26. Again, Desmos wants you to find these locations. It will probably stay on if you click on each one of them because it knows that these are crucial values on the graph of the function. Again, in order to see the relative maximum and the inflection point, we have to change the scale so much that we lose sight of the relative minimum. We can still see it, but it's hard to distinguish it from the x-axis. Let's now go ahead and take a look at example 5. In example 5, looks like I left way too much space there. We're looking at the natural log of 3x squared plus 1. We want to determine where it is concave up and where it is concave down. Go ahead and pause the video, work it out, and turn the video back on, and we'll compare. So let's compare our work. On this problem, note that the domain is actually all reals. We have to make sure the argument to natural log is strictly positive. But when we solve for the variable, we note that it's x squared greater than -1/3. All squared values are non-negative, 0 or higher, so they're always bigger than a negative. It tells me that it's true for all reals. Then I go ahead and I find the first derivative by invoking the chain rule with the derivative of natural log 1/u du dx. This gives me the rational function 6x divided by 3x squared plus 1. I look for critical points where the first derivative is 0 or the first derivative does not exist, but the function does. The denominator is never 0 because something squared at a minimum is 0. When I add 1, it never reaches the value of 0. So there are none coming from the second case. In the first case, the numerator equal to 0 gives me x equals 0 as a critical point. I didn't actually ask you to find the increasing decreasing. I'm just doing it to remind you of what the steps are. You could have gone straight to the second derivative. Then we go ahead and set up a sign chart, take test points on either side of the critical point, and find that it's decreasing and then increasing. That must mean that we have a relative minimum there at x equals 0. Then, in order to find the actual location of it, I have to substitute 0 into the original function, the natural log. This gives me natural log of 1, which is 0. The origin is, in fact, a relative minimum. Now the work you were supposed to do. You need to find the second derivative. First derivative is here. So in this case, I chose to do the quotient rule. You could have written the denominator to the -1 power and used product rule and chain rule instead. When I simplified, I got another rational function, -18x squared plus 6, all divided by the denominator squared. Now we need to find the critical points of the first derivative, where the second derivative changes sign or is undefined, but the first derivative is defined. To do that, I set the numerator equal to 0, and I got plus or minus 1 over the square root of 3, which is pretty close to plus or minus 0.6. There's no place where the denominator is undefined, so the second derivative always exists. When I set up a sign chart with these possible inflection points, take test points in the open intervals. I discovered that on the left side, from -infinity up to -1/√3, it's concave down. Between -1/√3 and 1/√3, it's concave up. And again, from 1/√3 to positive infinity, it's concave down again. With these pieces of information, along with some information from college algebra, I can draw a very accurate graph. Let's go ahead and look at the graph now. This is a kind of interesting function. I find it rather fascinating. It's difficult to tell exactly where the inflection point is without the calculus, but we know there have to be two because it's clearly concave down here and clearly concave up here, again changing to concave down. So the inflection points have to be there. I went ahead and I added the inflection points as well as the critical point to a table so that I could graph all of the points. Notice that we do have a relative minimum at the origin, and we have two inflection points, which are showing up here. In order to find the true value of the inflection point, we would need to substitute those values into the actual function. Let's go ahead and do that now. We'll start with the value x equal -1 over the square root of 3. To find the actual inflection point, I need to substitute that into the original function. The original function was f of x equal to natural log of 3x squared plus 1. When I take this negative 1 over root 3 and substitute it into the function, notice that it's squared, which means I'm going to get the same y value for positive 1 over root 3. This is going to give me the natural log of 3 times negative 1 over root 3 squared, which is positive 1/3. Then I multiply by 3 to get 1, and I end up with the natural log of 2. My inflection points are at plus or minus 1 over square root of 3, comma, natural log of 2. That's precisely where these dots on the graph occur. Let's now look at the last example in this section. Before we get there, let's go ahead and sum up what we've been looking at so far. If the sign of the first derivative is positive, it's increasing. And if the sign of the first derivative is negative, it's decreasing. If the sign of the second derivative is positive, it's concave up. The sign of the second derivative is negative, it's concave down. Notice that it also has some relationship one to the other. We have a relative minimum when we go from decreasing to increasing. Notice also that at that critical point, the graph is concave up. When we have a relative maximum, we've gone from increasing to decreasing. And notice that at that point, we have concave down. This is another way of determining where the location of the relative extrema are. If the function is concave up, strictly positive, at a critical point, you must have a relative minimum there. If the curve is concave down, strictly negative, at a critical point, you must have a relative maximum there. This is actually called the second derivative test. Let's now take a look at these graphs and locate where they're increasing, decreasing, concave up, and concave down. When we look at these, I'm going to make a chart so that we can tell which one is which. Increasing, decreasing, concave up, and concave down. Now we need some highlighting colors. And it looks like I need one more. Let's see. What would be a good contrasting color? Maybe gray. All right. When I'm looking at the graph, let's say we make every place it's increasing gray and every place it's decreasing yellow. When it's going to be concave up, we'll make it purple. And when it's concave down, it must be blue. When I look at these two graphs, again, I can tell most of this just by inspection. It's decreasing from -2 down to -1.5. So decreasing would be over this section right here. It's also decreasing here in this section and here in this section. The second graph is decreasing here and decreasing here. Where is it increasing? Well, it's increasing in between those places. Where is it concave down and where is it concave up? Let's do concave up first. It's concave up on this entire section here, all the way until we get to where it changes its curvature, which has to be about there. Now, it's also concave up in a small section in here But again, at the inflection points, it ceases to be concave up and becomes concave down. It's kind of hard to tell where this one is, but I'm going to guess it's about here. It's concave down then at the inflection point around to the next inflection point. In this graph over here, we have concave down until we get to the inflection point partway around. And then again over here, we have concave up in this section here. Oops, not that section. Concave up from here around to here. And again from that inflection point for the rest of the graph. Let's now take a look at the last example in this part, which is this graph here. When we're looking at this graph, let's also go through and talk about where it's increasing, decreasing, concave up, and concave down. We'll do increasing first. When we're looking at the graph and we want to know where it's going to be increasing, we can look at the graph and see that it's increasing on this section here from the relative minimum up to where we have an absolute maximum. It's also increasing again from the relative minimum to the right. It is decreasing in between from the left to the location of the relative minimum and from the absolute maximum to the location of the next relative minimum. Where, in fact, is it concave up? If we look at the concavity, remember that concavity can only change when the second derivative is 0 at an inflection point, or where the second derivative is not defined, but the first one is. We can see that it is actually concave up on both sections, but not right at 0, because the derivative does not exist at 0. And so it is neither concave up nor concave down there. We have a cusp. This graph is never concave down. Let's go ahead now and formally state the second derivative test. Let's take a look at the formal statement of the second derivative test. We'll have to be a bit more careful here because there is a condition under which it fails, and that is when the second derivative is 0, or when the second derivative is undefined, but the first derivative is. We only know that it is going to be concave up, provided the second derivative is strictly positive, and concave down, provided the second derivative is strictly negative. The second derivative doesn't exist, such as at a cusp or a corner, and we don't know what we have there. We'll have to look at the graph. If the second derivative is 0, we also don't know what happens there. Again, we have to use the first derivative test to figure out if we have something happening at that point. The second derivative test says basically that if the second derivative is positive and the first derivative is 0, it's a critical point, then it must be a local minimum. If the first derivative is 0, meaning that it is a critical point, and the second derivative is negative, concave down, then we must have a relative maximum. Notice the second derivative test does not address the points where the first and second derivative do not exist. When those happen, such as at cusps and corners, we have to go to the graph to see whether we have an extrema value. We're going to consider this function now, which is a new function for us. We're being told that the points 3 and -2 are critical points where the first derivative is 0. We want to use the second derivative test to determine whether it has a local max or a local minimum at those points. Let's go ahead and work this one together. When we look at this, we need to first, of course, find the first derivative. This is the polynomial, so we know the domain is all reals. When we find the first derivative, f prime, we get 3x squared minus 3x minus 18. Again, if we're looking for where the first derivative is 0, or the first derivative is not defined but the function is, that would give us the critical points. We're told what the critical points are, but let's go ahead and prove it by finding where the first derivative is 0. I can factor out the 3 to get x squared minus x minus 6 equals 0. This is going to give me x minus 3 and x plus 2. That gives me the two values they gave us as the critical points, 3 and negative 2. Notice that as a polynomial, the function is defined everywhere, and so is the first derivative. Let's take a look now at using the second derivative test without having to use the first derivative test. I want to test at the critical points by placing them into the second derivative. The second derivative is 6x minus 3. F double prime at 3 gives me 18 minus 3, which is 15. This is positive, which tells me that it's concave up there, so I must have a relative minimum when x equals 3. I don't know what the relative minimum is until I substitute it into the original function. When I test at the second derivative at the other critical point, negative 2, I get negative 12 minus 3, which is negative 15. That's a negative value, which tells me it's concave down, so I must have a relative maximum in the graph at x equals negative 2. Let's take a look at this graph and see what it looks like. You can see here that I do, in fact, have relative extrema at those locations. Again, if it turns out that the first derivative is 0 and the second derivative is positive, it must be a relative minimum. If the first derivative is 0 and the second derivative is negative, it must be a relative maximum. If the first derivative is 0, but the second derivative is 0, we don't know. Then we have to go to the graph and do the first derivative test. Let's now look at the last example in this section, example 8. We want to use all the information that we have learned so far. We want to know where it's increasing, where it's decreasing, where it's concave up, where it's concave down, where are the relative extrema, and where are the inflection points. This one is the function square root of x times natural log of x. I've already given you the domain, which is open 0 to infinity. Make sure that you test and make sure the critical points are in this open interval from 0 to infinity. Go ahead and pause the video, work it out, then turn the video back on, and we'll compare our massive results. So let's compare all of this work that you've done. We know the domain is open 0 to infinity. All critical points will have to fall in that interval. To find the first derivative, we applied the product rule with the chain rule. This led to a combined first derivative of 2 plus the natural log of x divided by 2 square root of x. Do not cancel the 2's because of the addition in the numerator. Now we look for the critical points. The first derivative is not defined when x is 0, but 0 is not in the domain, so it's not a critical point. There are no other points that are a problem for the first derivative. The first derivative is 0 when the numerator is 0, which means the natural log is equal to negative 2. switch to exponential form to get the critical point 1 over e squared, or e to the negative 2, which is about 0.135. Then we'll draw a chart which will allow us to determine where it's increasing and decreasing. When we're looking at increasing, decreasing, we split the number line with only the critical points to make tick marks. Then we choose something in the domain on the left and the right of that critical point. 0 is not in the domain, so I chose 0.1 on the left and 1 on the right. Remember to substitute those values into the first derivative. When I substituted them in, I got a negative on the left and I got a positive on the right, which told me it was decreasing on the left and increasing on the right. On an exam, I would expect you to write decreasing over negative infinity to 1 over e squared and increasing from 1 over e squared to infinity. To find a location of the relative minimum, it was going downhill and then up, I substitute the value of the critical point into the original function. When I do that, I end up with negative 2 divided by e. My relative minimum has that for the y value at the critical point. Now let's look at the second derivative. I rewrote the first derivative so I had something to refer to. Then I applied the quotient rule. You could also instead apply the chain rule and product rule if you put both the 2 and the square root of x in parentheses with a negative 1 power outside. When I simplified, I ended up with negative natural log of x divided by 4 times x to the 3/2 power. That's the square root cubed. To find the critical points of the first derivative, I look for where the second derivative is 0 or the second derivative does not exist, but the first derivative does. The only value that causes a problem in the second derivative is 0, but it's not in my domain, so it's not a critical value of the first derivative. Then I set the numerator equal to 0, which is negative natural log of x equals 0. Multiplying both sides by a negative eliminates that, and switching to exponential form tells me that a possible inflection point occurs at x equal 1. Then I draw a second number line to represent the concavity. I use the possible inflection point as a tick mark on the line. I take something in the domain to the left, 1/2, and something in the domain to the right, 2. I substitute those values into the second derivative equation, and I got a positive on the left, meaning it's concave up, and a negative on the right, meaning it's concave down. Go ahead and write the interval over which it's concave up as negative infinity to 1, and the interval over which it's concave down as 1 to infinity. As the concavity changes, I know that I have an inflection point. Then I substitute the value of 1, the inflection point location, into the original function to get the y value, which turns out to be 0. Let's put all of this together and take a look at the graph. It took quite a bit of graphing to get it on here. If you're looking at this graph and we scroll in, we'll see that it is defined for all values up to 0, but not defined at 0. It gets very, very vertical here. Not quite vertical, but close to it. We can see that there is definitely a relative minimum here at 1 over e squared. I added this to my table of values so that I could locate it. When I look over here, if I scroll back out again, it's very difficult to tell, to be honest, that there is a change in curvature there. I can't really tell that it changes from concave up to concave down, but I can compute it using calculus, and I know that at 1, 0, it ceases to be concave up and becomes curved down. It's It's a very slight change and not one we would find with the naked eye. In the next video, we'll learn one last technique for helping to draw the graph of a function. We'll use everything we've learned from algebra and calculus now to put it all together. The one last thing we want to learn is when we have an oblique asymptote. In other words, it's not going to infinity except by following a slanted line. We'll also take a look, just for fun, at some that follow different types of functions. I hope to see you for the next video.